Hi, and welcome to this tutorial about linear phase EQ. FabFilter's Pro-Q plugin offers a selection of linear phase modes with progressively higher latencies. It would be reasonable to assume that the default minimum phase mode is the lowest quality setting, and the setting with the highest latency provides the highest quality. It's not as simple as that, however. While the high and max latency linear phase modes do indeed provide better quality than the lower latency linear phase modes, in most situations the default zero latency mode will actually perform better than any of them. Let's start with a kick drum, which I've created using Twin 2 running through Saturn, and which I've sculpted heavily with EQ. Working from the left, I have a high-pass filter to remove the very lowest frequencies, but also with some resonance to create a boost at about 50 Hz. Then a steep, sharp notch filter at just below 90 Hz to make room for some important frequencies in the bass guitar part, plus a wide, deep cut at 500 Hz to remove some stuff I just don't like. Let's solo the kick channel and switch to the maximum latency linear phase mode. And notice the difference this has made to the initial transient. Instead of starting with a solid clicky attack, each hit is now preceded by a short crescendo of the low boomy part of the sound, almost like a reverse reverb effect. If I switch back to minimum phase zero latency mode, each kick drum hit now starts with a clicky attack again, and the low boom follows afterwards as it should. So what's actually going on here? I can demonstrate it visually using a special impulse signal known as a Dirac spike, which is simply one single full-scale sample in a file full of zeros. If I process this with a low-pass filter in zero latency mode and render the result, we can see that the filter rings for a short period after the original spike. Processing again in linear phase mode produces a similar ringing effect, but this time it starts before the original transient and continues afterwards. This might seem to be impossible until you remember that the linear phase modes all introduce an overall delay to the signal, which has been compensated for automatically by the DAW. It is this pre-ringing that accounts for the transient smearing effect in my kick drum example. Pre-ringing tends to be much more noticeable than the post-ringing effects caused by minimum phase filtering, and is a general problem with all linear phase algorithms, not just those in Pro-Q. I confess, I've manufactured this example deliberately to make the pre-ringing as obvious as possible, by applying fairly drastic low-frequency EQ shaping, and by choosing a source that combines lots of low-frequency energy with a hard transient attack. In most cases, pre-ringing will be much more subtle than this. So, we have an example of linear phase mode definitely not being an improvement over zero latency mode. But in what situation would linear phase be useful? Well, perhaps I should first of all clarify what we mean by the term phase in the first place. Let's take a simple sine wave, the basic building block of all sounds, just one pure frequency, in this case at 200 Hz. And I'll duplicate the track to create an exact copy. Adding these together results, much as you would expect, in an identical sine wave with twice the amplitude, equivalent to a gain boost of 6 dB. Now notice what happens if I slide the copy later. The resulting sine wave gets quieter and quieter, until we reach the point where the peaks in the copied waveform line up with the troughs in the original, and the two cancel out completely. By changing the timing of the second waveform, I've changed its phase relative to the first waveform, phase being the term we use to describe how far a wave has travelled through its cycle. If I continue to slide the copy back in time, the two sine waves will stop cancelling out, and we'll eventually come back full circle with both waves in phase with each other again. Like a circle, we measure phase in degrees, So when two waves are equal and opposite to each other, we say that they are 180 degrees out of phase, while 360 degrees of phase shift puts us back where we started, with both waves perfectly in phase again. Of course, another way to create a phase shift of 180 degrees would be to invert the polarity of the wave so that positive cycles become negative and vice versa. And our two sine waves now cancel out again. So we can see that when mixing two identical or very similar waves together, the phase relationship between the two waves will have a profound effect on the result. A commonly cited example of this would be a drum kit recording using multiple microphones. The example you see here is a short multi-track drum loop played by Stefano Esposito and recorded with a total of 8 mics. When considering the sound of the snare drum, we therefore have to take into account the contributions from both top and bottom snare mics, the overheads, and the single room mic, and also the phase relationship between them. If I solo the snare close mics individually, we hear that they sound quite different. But being two mics pointing at the same snare drum, there are also many similarities between the two. Or in other words, the two signals are correlated. If I solo both mics together and invert the polarity of just the top snare using the phase button on the mixer channel, the combined sound changes noticeably, and the low fundamental of the drum is much reduced in level. So let's put the mics back in phase with each other, add a Pro Q to the top snare channel, and try applying some typical EQ shaping, perhaps to address the ringing at around 400 Hz. And actually, it works much as you'd expect. Boosting that frequency makes the ringing louder and more prominent, while cutting tames the ringing and makes the snare sound tighter and more damped. If I switch to linear phase, the difference is very subtle. Let's load Pro Q into an analyzer to try to see what's going on. This is Christian Budd's free VST plugin analyzer software, and I'm going to choose to measure the plugin's frequency response. This produces a graph much like the one on Pro Q's own interface, and any changes I make to the EQ settings are mirrored by the analyzer after a short delay. The analyzer can also be set to measure phase response, however, via the domain menu at the top. And the graph now displays the phase changes caused by the EQ cut I dialed in. As expected, switching to a linear phase mode results in a perfectly flat line, indicating no phase shifts at any frequency. But there are some interesting points to note about the phase shifts caused back in minimum phase mode. These shifts are both positive and negative, and they vary in proportion to the amount of gain I dial in for the band. If I boost instead, they swap over. But notice that the center frequency I'm targeting with the EQ remains at 0 phase all the time. In fact, the biggest phase shifts happen when the gradient is steepest on the EQ curve, not at the frequency with the greatest cut or boost. If I switch to a low shelving filter instead, this time we have a single phase shift, again centered on the region with the steepest gradient, and the phase trends back towards 0 in the flat regions above and below the shelf. So I'm now going to analyse the frequency response again, but this time for a parallel signal chain in which the output from the EQ is added back together with the original signal. With no EQ applied, we simply have a doubling of amplitude, so an overall volume boost of about 6 dB. And applying an EQ cut results in a slight dip at that frequency, as I cut it out of just 1/2 of the signal path. Let's switch to linear phase, and notice that the overall amount of cut applied doesn't change, as our target frequency is at 0 phase in either case. Instead, the differences occur where the phase changes are greatest above and below the target frequency. So the overall result is just a narrowing of the bell shape. Quite a subtle difference, which can be almost completely dialed out by adjusting the Q to compensate. Likewise, if I switch the EQ shape to a low shelf, again the overall effect is much as you'd expect. And the difference between linear phase and minimum phase amounts to just a slight difference in the slope and the frequency of the shelf. So what's going to happen if I choose a high-pass filter instead? Well, in linear phase mode, the results are again much as you'd expect. The signal starts at unity, coming only from the dry signal path. Then the level rises smoothly as the high-passed signal starts to contribute, with an overall shape like a high shelving boost. If I switch to minimum phase, however, we now see quite a dramatic difference, with a steep notch suddenly appearing near the cutoff frequency. If we look at the phase response of the high-pass filter, we can see why. Unlike the subtle, gentle phase shifts from the bell and shelving filters, the high-pass filter has a dramatic effect on the phase, with a full 180-degree phase reversal at the cutoff frequency. So let's go back to our snare drum example. Still listening to a mix of both top and bottom snare mics, and dial in a high-pass filter for the top mic instead of a bell. Sweeping the filter up from the low frequencies, we start to hear the low fundamental of the drum drop in level, even though we've not reached high enough to be reducing that frequency with the filter at all. If I solo the top snare on its own and toggle the filter in and out, we don't really hear any difference. But with both mics on, there is definitely a difference. This is, of course, because the high-pass filter has applied almost exactly 180 degrees of phase shift to those frequencies, and therefore changed the way the two signals mix together. I can prove this by reversing the polarity of the top snare using the channel phase button again. And unlike before, the low fundamental of the drum is now much stronger with the top mic flipped. Switching to a steeper filter will result in even more unpredictable side effects. With a 48 dB per octave filter, set a little below 180 Hz, we find the ringing frequency we identified earlier has suddenly disappeared completely. If I bypass the filter, it comes back. Filter back in and it's gone again. If I switch to linear phase mode, however, this ringing frequency is not affected. The filter cuts out the low bass without affecting the way the two snare mics mix together. Back to the analyzer again, and we can clearly see the massive notch in the frequency response that's killing the snare drum ring. But in linear phase mode, the dry and wet signals combine together with no unintended side effects. It's still not entirely clear which mode is better, however, even in this example. Linear phase mode produces more predictable results by avoiding changing the phase relationship between correlated signals. But changing the phase relationship between correlated signals is not necessarily a bad thing, and in some cases might help them fit together in subjectively more pleasing ways. I'm going to manufacture a more extreme example for you. Let's route the kick and the bass parts from my earlier example to another channel. Then low pass filter this channel down to about 100 Hz to isolate the low bass. And add a Pro C set to compress the results quite hard. Mixing this signal in under the rest of the mix should create a frequency-specific upward compression effect, like the one I used for the high frequencies in the mastering tutorial series. To glue the kick and bass parts together, and to add weight to the whole mix. However, while adding in this channel seems to raise the level of the kick in the mix, it's not really helping the bass at all. Until I switch to linear phase mode. This time the difference is pretty clear. Linear phase mode sounds much better than minimum phase in this situation. Again, the analyzer shows us why. In a parallel configuration, the phase shift from the minimum phase filter causes a steep notch to appear near the cutoff frequency, and this was a critical region for the bass guitar sound. No such notch appears in linear phase mode. However, minimum phase filters still have some uses even in this setup. I'll turn down the Q for the filter to produce a more gentle slope. And notice that the dip in the overall frequency response is now much reduced. In fact, it begins to resemble the Curzon shape, which combines a shelving boost with a cut just above it, and which can sometimes sound better than just a simple shelf EQ. So let's tune the cutoff frequency higher to about 500 Hz. The frequency response now dips around 500 Hz, a region that's not that important to either the kick or the bass sounds in this case, and then rises smoothly in the low end. Switching back to our kick and bass example, it's no longer obvious that linear phase is better. In fact, I might now prefer the results in minimum phase mode. Of course, it's also worth considering the fact that I'm running a compressor on the signal, so the level of the filtered signal will also be changing relative to the dry signal. The easiest way to see this in the analyzer is to adjust the level of the wet signal using ProQ's own output level knob. When the kick and bass levels are high, the compressor will be reducing the gain of the filtered signal, so the overall frequency response will flatten out. Then, when the compressor releases, the levels will increase again, so boosting the low frequencies and cutting the mids. In other words, we've created an upward compression effect for the low frequencies, and also a downward expansion effect for the mid frequencies above it. In linear phase mode, however, there is no downward expansion of the mids. We are now just purely compressing the low end. So, in summary, most of the time, for conventional EQing duties, the minimum phase mode will be the optimum choice, as well as being conveniently free of latency. The linear phase modes are more specialised options that will behave more predictably and intuitively when mixing correlated signals, but might not necessarily sound better. Regarding the different latency options, most DAWs will compensate for latency when mixing, so you can safely choose the better quality high and max settings when you need a linear phase option. If latency is an issue, try progressively lower settings and listen out for any unwanted artifacts, especially when dealing with low frequency content. That's all I have time for in this video. Thanks for watching.